In this video, we're going to integrate some functions into log functions by using U-substitution, some long division, and some trig function integration. Let's get started. Let's start off with the parent rational function, which is 1 over x. When we integrate 1 over x dx, we end up with the natural log of the absolute value of x plus c. This is what we see on top here in green and in blue, but in terms of u rather than in terms of x. They're exactly the same function. Let's look at one more example, but instead of 1 on top, let's look at an example where the numerator is 4 rather than x, rather than 1. So we integrate 4 over x dx. We can take the 4 outside since it's a constant. 4 integral of 1 over x dx. This gives us 4 times the natural log of the absolute value of x plus c. One more example would be negative 3 over x dx. Let's take out the negative 3 in the front since it's a constant. We write negative 3 integral of 1 over x dx, which is equal to negative 3 times the natural log of absolute value of x plus c. Let's look at one more example where it's 1 over x minus 9 dx. Now the denominator is no longer just x, it is now in terms of a linear function, which is ax plus b or mx plus b. In this case, if we want to use a shortcut, we can use this function here, which I will show you later on. But let's start by using U-substitution. We'll let the denominator be u. So we have u equals x minus 9. Take the derivative of both sides with respect to x. So du over dx is the derivative of u equals the derivative of x, which is just 1. Cross multiply, we end up with du equals dx. So the function to the left becomes the integral of 1 over u, and dx is now du. This simplifies to natural log of the absolute value of x plus c, rather u, that's my mistake, let's make it u plus c. And we substitute this u in here to finalize the answer. So we end up with natural log of the absolute value of x minus 9 plus c, and that's the final answer. Let's look at some more examples. Let's do integral of 7 over x plus 2 dx. Since 7 is a constant, the 7 can go outside the integral. So we write 7 integral of 1 over x plus 2 dx. Now, we let u be the denominator. So we write u equals x plus 2. The derivative is du over dx equals to the derivative of x, which is just 1 plus 0. Cross multiplying, we get du equals dx. We write 7 integral 1 over x plus 2 becomes 1 over u du. And this is equal to 7 times the natural log of absolute value of u plus c. And since u equals x plus 2, we substitute this in here. So we get 7 times the natural log of the absolute value of x plus 2 plus c. Notice how 7 on top is a constant that is not 1. In this case, we can use the equation in orange. So this one will be equal to k over a. In this case, k over a will be 7 over 1. So we write 7 over 1 times the natural log of the denominator, the absolute value of the denominator. So times the natural log of the absolute value of x plus 2 plus c. And this is exactly what we got earlier here as a final answer. One more example would be integral of 10 over 2x minus 1 dx. We can use this shortcut right here in orange, so we don't have to use U-substitution. Let's try it right now. This would equal k over a would be k on top, which is a constant, which is 10, over a, which is 2. So let's go back and write 10 over 2 times the natural log of the denominator. So times the natural log of the absolute value of 2x minus 1 plus c. If we simplify this, we get 5 times the natural log of the absolute value of 2x minus 1 plus c. And that's our final answer. Let's do it by U-substitution. So we start off with the integral of 10 divided by 2x minus 1 dx. We write u as the denominator, which is 2x minus 1. We derive with respect to x. The derivative of u with respect to x is du over dx is equal to the derivative of 2x is 2 minus the derivative of 1, which is 0. We switch these two to solve for dx. Now the reason the switching works is because, let's say I give you something like 10 divided by 2. 10 divided by 2 is equal to 5. If we switch these two, we end up with 10 divided by 5 is equal to 2. So the switching works because 5 times 2 or 2 minus 5 will end up giving you 10 anyway. So now we switch these two and we end up with du over 2 is equal to dx. So the integral becomes 10 over 2x minus 1, which is now u, times dx, which is now du over 2. So we write du over 2. 10 divided by 2 is 5. So we can write 5 over u du. And since 5 is a constant, we can take the 5 outside. We end up with integral of 1 over u du. And the integral of 1 over u is natural log of u plus c. Now we just have to integrate the u back in here. And we end up with 5 times the natural log of 2x minus 1 plus c. And if we notice on top here, we got the same answer. Let's do the integral of 4x divided by x squared plus 11 dx. In this case, the denominator is not a linear function, so we cannot use any of these functions here to simplify without using U-substitution. So we'll still have to use U-substitution. We'll say, let u be the denominator, which is x squared plus 11. The derivative in terms of x would be du divided by dx is equal to the derivative of x squared is 2x, and the derivative of 11 is 0. We switch these two, and we get du over 2x equals dx. So now we write the original function in terms of u. We have integral of 4x all over u, because that's x squared plus 11, times dx, which is now du over 2x. We simplify by dividing the x's. X cancels with x here. And 4 divided by 2 is 2. So this becomes the integral of 2 over u du. The 2, which is a constant, can go on the outside of the integral. So we write 2 times the integral of 1 over u du. And the integral of 1 over u du is just ln of u plus c. So we write 2 times ln of the absolute value of u plus c. And since u is x squared plus 11, we can substitute this in here to get the final answer, which is 2 times the natural log of the absolute value of x squared plus 11 plus c. That's your final answer. Here's another example. Let's do the integral of x squared plus 2x minus 4 all over x dx. In this case, we can separate this into 3 different fractions by writing each of the numerator elements over x on the bottom. So this will be the integral of x squared over x plus 2x over x minus 4 over x dx. Let's simplify this. X squared divided by x is just x, plus 2x divided by x, the x's cancel, we end up with 2, minus 4 over x, we're going to keep it as 4 over x. We're not going to bring the x to the top and give it a negative exponent. We'll keep it on the bottom because this ends up being a natural log integration. So we integrate now, and the integral of x is x squared over 2, plus the integral of 2 is 2x, minus 4 over x would be 4 times the natural log of x, plus c. That's the final answer, but you can write it as 1/2 x squared plus 2x minus 4 natural log of absolute value of x plus c. And that's the final answer. Here's another example. Let's do the integral of natural log of x all to the power of 5 all over x dx. Notice how the derivative of ln of x is 1 over x, which is right over here, 1 over x. So we'll let u be natural log of x. U equals natural log of x. The derivative on both sides is du over dx equals the derivative of ln of x is just 1 over x. We cross multiply, we get x du equals 2 dx. Now we write this in terms of u. So we end up with u integral of u to the power of 5 all over x times dx, which is x du. We simplify by cancelling the x's out, and we end up with the integral of u to the power of 5 du. When we integrate u to the power of 5, we end up with u to the power of 6 over 6 plus c. This can be written as 1 over 6 u to the power of 6 plus c. We substitute natural log of x in for u to simplify in terms of x. So we end up with 1 over 6 times natural log of x to the power of 6 plus c. And that's our final answer. Let's do one more example. Integral of 4x minus 2 all over x plus 2 to to the power of 2 dx. In this case, again, the denominator is not a linear function, so we cannot use any of the functions on top here. So we'll let u be the denominator without the squared. U equals x plus 2. The derivative of u is du over dx equals to the derivative of x plus 2 is just 1. We cross multiply, we end up with du equals dx. So this function can be written as the integral of 4x minus 2 all over u squared times dx, which is now du. So we have the function in terms of u, however, we have an x here that we haven't gotten rid of. So what do? Since u is equal to x plus 2, let's solve for x here. We subtract 2 on both sides and we end up with u minus 2 equals x. Now I can take this here for x and I can substitute it in for x here. So I'll end up with the integral of 4 times x, which is now u minus 2, minus 2, this minus 2 is right here, all over u squared, du. This simplifies to the integral of 4u minus 8 minus 2 all over u squared du. Let's simplify this. We end up with integral of 4u minus 10 all over u squared du. So we end up with integral. We can separate it into two different fractions. We have 4u over u squared minus 10 over u squared du. Simplifying further, we end up with the integral of 4 over u minus 10. We can take the u up to the numerator and ends up being u to the power of negative 2 du. Integrating, 4 over u ends up being 4 times the natural log of the absolute value of u minus 10 times u to the power of, we add 1 to the negative 2 in the numerator, becomes negative 1, and then we divide by that negative 1, plus c. This ends up being 4 natural log of absolute value of u. Negative and negative here become a positive. So plus 10 times u to the power of negative 1, which can go into the denominator as u to the power of 1, plus c. We now substitute u equals to x plus 2 into the equation to simplify. So we end up with 4 times the natural log of x plus 2 plus 10 divided by x plus 2 plus c. Here's another example. Let's do the integral of x plus 2 divided by x squared minus 3x minus 10 dx. In this case, you always want to try to factor the numerator or the denominator to see if you can simplify. The denominator is simplified and factored. We end up with x squared minus 3x minus 10. Now, what two numbers multiply to give us negative 10 and add to give us negative 3? Taking the denominator, let's try to factor it. We end up with x squared minus 3x minus 10. And we're trying to find two numbers that when multiplying, they give us negative 10, and when adding, give us negative 3. Let's look at the factors of negative 10. Negative 10, we have 1 times 10 and 2 times 5. The two numbers that add up to negative 3 are 2 and minus 5. So this simplifies and factors to x plus 2 and x minus 5. So the integral becomes the integral of x plus 2 divided by x plus 2 times x minus 5 dx. We can cancel the x plus 2 and x plus 2 and simplify. This becomes integral of 1 over x minus 5 dx. This ends up being natural log of the absolute value of x minus 5 plus c. And that's the final answer. Let's look at some more examples. Let's do the integral of 3x squared minus 2 all over x cubed minus 2x dx. Notice how the denominator has a derivative of 3x squared minus 2. And that's exactly what we have on top in the numerator. In this case, we can use U-substitution. So let's do that. We say let u be the denominator, which is x cubed minus 2x. Take the derivative of both sides. We end up with du over dx equals to 3x squared minus 2. So now we write this function in terms of u. We have 3x squared minus 2 divided by x cubed minus 2x is now u. So we put u on the denominator. And dx, we have to switch these two to get dx. So let's do that. Du divided by 3x squared minus 2 is equal to dx. So this function right here, we multiply by dx, which is now du over 3x squared minus 2. So that's du over 3x squared minus 2. We simplify by dividing the 3x squared minus 2 into itself, so they cancel. And this simplifies to the integral of 1 over u du. This equals to natural log of the absolute value of u plus c. And since u is equal to x cubed minus 2x, we write natural log absolute value of x squared minus 2x plus c. And that's the final answer. Here's another example. Let's do the integral of secant squared x divided by tan x dx. Now, from our knowledge of taking the derivatives, the derivative of sine of x is equal to cosine of x. And the derivative of cosine of x is equal to negative sine of x. Tan of x, the derivative is secant squared x. And the derivative of tan x is secant squared x. So we can use U-substitution. So we say let u be tan x, which is the denominator. Taking the derivative, we end up with du over dx equals to secant squared x. Switch these two, we end up with du over secant squared x equals dx. This ends up being integral of secant squared x divided by tan x, which is now u, times dx, which is du over secant squared x. The secant squared cancels with the secant squared in the denominator. So we have integral of 1 over u du. And this simplifies into natural log of the absolute value of x plus c. Rather, u plus c. And u is tan x, so we can substitute the tan x in here. We end up with natural log of tan x plus c. And that's the final answer. One more example would be the integral of x plus 1 divided by x squared plus 2x dx. Now the derivative of the denominator is 2x plus 2, which is not exactly what we have in the numerator, but if we factor out the 2 here, we end up with 2 times x plus 1. And since this is a numerator, we can use U-substitution. So let's do that. Let u equals to x squared plus 2x. Take the derivative of both sides, we end up with du over dx equals to, the derivative of x squared is 2x, and the derivative of plus 2x is plus 2. We now write this function in terms of u, so we have integral of x plus 1 all over u times dx, which is du over 2x plus 2. And how did I get this? Because I would switch these two here to get du over 2x plus 2 equals dx. And that's what I substituted in here for dx. Now in this case, because these aren't the same, I can't just cancel them. So what I have to do is I'd have to factor out the 2 in the denominator right here. So then we have integral of x plus 1 all over u times du over, factor out the 2, we end up with 2 times x plus 1. The x plus 1's cancel, and the 1 over 2 here can go on the outside of the integral. So we have 1 over 2 integral of 1 over u du. And this simplifies to write 1/2 times the natural log of the absolute value of u plus c. And since u is x squared plus 2x, we write 1/2 natural log of x squared plus 2x plus c. And that's the final answer. One more example would be the integral of 1 over x times the natural log of x dx. And since the derivative of ln of x is 1 over x, we can let u equals to ln x. So let's do that. U is equal to ln x. The derivative would be du over dx equals to 1 over x. If we cross multiply, we end up with x times du equals to dx. Let's write the function now in terms of u. We have integral of 1 over x times natural log of x, which is u, times dx, which is now x times du. We can cross out the x's and rewrite the function in terms of u, which is 1 over u du. And the integral of 1 over u du is a natural log of the absolute value of u plus c. And since u is equal to ln x, I can substitute this in here. And I get ln of the absolute value, natural log of x plus c. That's the final answer. Another example, the integral of x divided by square root of 9 minus x squared dx. In this case, the denominator has the square root of 9 minus x squared. If we let u be 9 minus x squared, the derivative of 9 minus x squared is negative 2x. And since this is a multiple of this, we can use this whole thing as u. So that's what we're going to do. So we let u be 9 minus x squared without the square root. Take the derivative of both sides with respect to x. So du over dx is equal to the derivative of 9 is 0, and the derivative of negative x squared is minus 2x. Switch these two. We end up with du over negative 2x is equal to dx. So we write this in terms of u, we end up with integral of x over the square root of u times dx, which is now du all over negative 2x. We cancel out the x's, and 1 over negative 2, we can take it outside as a coefficient. So we have negative 1/2 integral of 1 over the square root of u du. We have negative 1/2 integral 1 over the square root of u can be written as 1 over u to the power of 1/2 du, which is negative 1/2 integral u to the power of 1/2 can be brought up, and you write u to the power of negative 1/2 du. When we integrate, we add 1 to the exponent, so we end up with u to the power of 1/2 divided by 1/2 plus c. This simplifies to negative 1/2 times, when you divide by a fraction, you flip it and you multiply by its reciprocal. So times 2 over 1 times u to the power of 1/2, which is the square root of u, plus c. The 2's cancel, and we simplify into negative the square root of u plus c. And since u was 9 minus x squared, we simplify by substituting that back in here, 9 minus x squared plus c. And that's the final answer. One more example, integral of 1 over x to the power of 2 over 3 times 1 plus x to the power of 1 over 3 dx. Now we're going to take the inside here as being u. So we let u equals to 1 over x to the power of 1/3. And you'll see when we take the integral, when we take the derivative rather, you'll see why we choose this as your u, because the derivative of this will end up being 1 over x to the power of 2 over 3. So the derivative of u is du over dx equals the derivative of 1 is 0, and the derivative of x to the power of 1/3 would be 1/3 x to the power of negative 2/3. We write this, we simplify, we write du over dx equals to 1 over 3 x to the power of 2 over 3. If we cross multiply, we end up with 3 x to the power of 2 over 3 du equals to 1 times dx is just dx. So we write this function in terms of u. We have integral of 1 over x to the power of 2 over 3 times u dx, which is now 3x to the power of 2/3 du. The x to the power of 2 over 3 here cancels with x to the power of 2 over 3. And we have a 3 here that's a constant that we can take outside. So we write 3 times the integral of 1 over u du. And this becomes 3 times the natural log of the absolute value of u plus c. This simplifies to 3 natural log of absolute value of u, and u is 1 plus x to the power of 1/3. So we plug that in here, 1 plus x to the power of 1/3 plus c. And that's the final answer. Let's look at one more example. Write the integral of tan x dx. Now, the integral of tan x dx is not something that you memorize unless your teacher tells you to. So we're going to write tan as sine x over cosine x, which is a rational identity, dx. Now, we know that the derivative of cosine of x is negative sine of x, and which is what we have on top here, without the negative, but we can work with that. So we let u be cosine of x. We say u equals cosine of x. Let's take the derivative of both sides. We end up with du over dx equals to negative sine x. Switch these two. We end up with du over negative sine x is equal to dx. We write this in terms of u, so we end up with integral sine of x divided by cosine of x, which is u, times dx, which is now negative du over sine x. The sine x and the sine x cancel. We're left with negative 1. We can take that outside, so we end up with negative integral of 1 over u du. Integrate 1 over u, and we end up with negative natural log of the absolute value of u plus c. And we substitute u, which is cosine x, into the equation to simplify. In terms of x, we have negative natural log of tan of x plus c. And that's our final answer. Here's another example. Let's do the integral of secant x dx. Now, in this case, is a special case where we're going to have to multiply secant x by something else to find the integral. Remember that the derivative of secant x is secant x tan x, and the derivative of tan x is secant squared x. So we're going to multiply this secant x by secant x plus tan x all over secant x plus tan x dx. Expanding this into these two and distributing the secant x into both, we end up with the integral of secant squared x plus secant x tan x all over secant x plus tan x. Now, the reason we did this is, if you notice that the derivative of secant x is secant x tan x, like we have up here, and the derivative of tan x is secant squared x, which we have up here. So we're going to let u be the denominator. All right, u equals to secant x plus tan x. We take the derivative, right? Du equals the derivative of secant x is secant x tan x plus the derivative of tan x is secant squared x. And this is divided by dx. Switching these two, we end up with du all over secant x tan x plus secant squared x equals to dx. So we substitute and write this in terms of u. We have integral of secant squared x plus secant x tan x all over secant x plus tan x. Rather, this is u, so we write u on the denominator, times dx, which is du over secant x tan x plus secant squared x. This ends up canceling with this. So we have integral of 1 over u du. And the integral of 1 over u du is the natural log of the absolute value of u plus c. And u is secant x plus tan x. So this becomes natural log of the absolute value of secant x plus tan x plus c. That's the final answer. Now let's finish this video up with an integral that requires partial fractions. Let's do the integral of x all over x minus 2 times x plus 3 dx. The denominator is already factored for you, but if it wasn't factored, you would have to factor it yourself. Now, before we take the integral, let's look at just this part right here and write it as a sum of two different fractions by using partial fractions. It's called partial fraction decomposition. So we have x over x minus 2 times x plus 3 is equal to a divided by, you take one of the two factors, which is x minus 2, you put it in the denominator here, plus b over x plus 3, which is the other factor. Now we'll find the common denominator. So we write x over x minus 2 times x plus 3 is equal to a over x minus 2. Leave a bit of a space and write b over x plus 3. Since we want the common denominator, I'm going to multiply this here by x plus 3, top and bottom, and multiply this one by x minus 2, top and bottom. So now we have the same denominator everywhere. And when you have an equal sign and you have equal denominators everywhere, you can just cross out the denominator completely and get rid of it. This simplifies into x equals to a times x plus 3 plus b times x minus 2. Now to solve for a and b, we're going to assume that x is equal to -3 first to get rid of this one. And then later we're going to assume that x is equal to 2 to get rid of this one here. So let's do that. So first we say let x equals -3. We'll substitute this -3 in here for every x value. We end up with -3 equals a times -3 plus 3 plus b times -3 minus 2. This simplifies to -3 equals to a, -3 plus 3 is 0, plus b times -3 minus 2 is -5. -3 is equal to a times 0 is 0, plus b times -5 is -5b. To solve for b, we divide both sides by -5. We end up with b equals to 3/5. That's our b value. Now next, we're going to get rid of the b value by assuming x is equal to 2. So we say let x equals to 2. This one, we substitute x equals to 2. We end up with 2 equals a times 2 plus 3 plus b times 2 minus 2. And since 2 minus 2 is 0, we have a, 2 plus 3 is 5, plus b times 0 is just 0. Divide both sides by 5. We have a is equal to 2/5. We're going to substitute these two values in this function right here. So let's copy this. And we're going to copy this part right here. And we're going to integrate this function with respect to x. We're going to substitute a and b. So we have integral of a, which is 2/5, times x minus 2. When you have a fraction and you plug it in, you put the fraction and you put the denominator into the other denominator. So the 5 goes next to the 5, x minus 2. Plus b, which is 3/5. So it's 3/5 x plus 3 dx. We can write these as two different integrals. So we have integral of 2/5 x minus 2 dx plus the integral of 3/5 x plus 3 dx. 2/5 is a constant. We can take that outside. So we have 2/5 integral of 1/x minus 2 dx plus 3/5, which goes outside as a constant, integral of 1/x plus 3 dx. We simplify, we end up with 2/5, and the integral of 1/x minus 2 is natural log of x minus 2 plus c plus 3/5, natural log of the absolute value of x plus 3 plus c. And that's the final answer.